So what is the projectivization of an affine curve? I will do some concrete examples in a moment, but let me just talk generally of what's happening. An affine curve, it's some curve in the plane that is given by some algebraic equations. And then those algebraic equations, there are solutions, numbers that satisfy those equations, and those are points on the affine curve. But then there's some times where we can see that if you follow the curve to infinity, there should be some points at infinity that we're sort of missing. And the projectivization, we add those points at infinity to the curve, and then the projective curve will be the affine curve plus those points at infinity that we were missing. And that is the projectivization. And then out of a projectivization or out of a projective curve, we can map down and see again some affine charts of that curve where we can see all the possible points in some sort of like affine charts, affine pieces of those curves. So we do both things. We start with an affine curve and we find the projective curve. And then from a projective curve, we also do affine charts. So let's do both things. Let's start with the projective plane P2, which is given in projective coordinates x, y, z. In projective coordinates, it means that this point and any scalar multiple of this point is exactly the same point. So x, y, z is the same as the point 2x, 2y, 2z. Now look at a chart, which is the chart where the z-coordinate is non-zero. That's a subset of projective points in the plane. Those with projective coordinates where this is a non-zero value. If this is non-zero, I can divide through by z, so I can scale this by z to get that that point is exactly equal to this point. But with the benefit that now, because this is fixed to be a 1, there's only one scale multiple of this that has a 1, so there's a unique way to parameterize those points, which is any x, any y, and a 1. Now, since these are the points on that chart, these are in bijection with the affine plane where there are just traditional coordinates x and y. So this chart is just the affine plane. So this is then what we call an affine chart of the projective plane. And now we're going to use that to find affine charts of curves. So start with a curve that is in projective coordinates. So you see it's given by a homogeneous polynomial in 3 variables. That curve, I'm going to take a chart. The chart z is not 0. And since z is not 0, I can simplify this. I can divide through by z squared and get a square minus a square equals 1. Now we have seen that those points, the points on that chart, are actually in bijective correspondence with points on the affine plane. And using the same correspondence, what we see is that the points on the projective curve in this chart, they're actually in bijection with the points on this affine curve, x squared minus y squared equals 1, this hyperbola. So this is a projective curve, and this is an affine chart of that projective curve. Or if you want, this is an affine curve, and this is the projectivization of that affine curve. Now let's go backwards. Let's start with an affine curve, and I want to find the projectivization. So to do that, I imagine this is an affine chart of a projective curve, and using the same identification I had before, that little x would be the projective x divided by z, and the little y would be the projective y divided by z. So plug those back in and simplify by multiplying through by z squared, and then I'm going to get this equation. And this equation is the projectivization of that curve, because this is an affine chart of that one. And then you see that in the points when z is non-zero correspond to the points in that affine chart, but there are more points in here. When z is 0, I've added 2 more points, because when z is 0, x squared would be equal to y squared, so x is plus or minus y, and that gives you 2 points at infinity. The point 1, 1, 0 and the point 1 minus 1, 0. Those are new points that were not present in here because they are at infinity in the graph of that hyperbola. Let me give you one more example. It starts with this affine curve, and I want to find the projectivization. I do the same business of calling little x in terms of projective coordinates, plug those in here, and I get this equation. Simplify by multiplying through by z cubed, And when I multiply by a z cubed, I get this equation, which is the projectivization of that cubic curve in the plane. Are there more points at infinity? Those are the points in the chart z is non-zero. Those are the points that are in here when z is non-zero. So what about when z is 0? Are there points at infinity? When z is 0, this is 0, that's not 0, that's 0. So what I get is that 0 equals x cubed. So x has to be 0. But there is no condition on the y, so there is one point at infinity that is missing, and that's the point 0, 1, 0. So this curve, which is actually an elliptic curve in projective coordinates, the points on this curve are those on the affine model, and one point at infinity, 0, 1, 0.